preceded by the escape character. On machines running Microsoft Windows, prior to the implementation of the Windows key on keyboards, the typical practice for invoking the Start button was to hold down the Control key and press Escape. This process still works in Windows 95, 98, ME, NT4, 2000, XP, Vista, 7, 8, and 10. Enter key or return key. Main article, Enter key. The Enter key, Enter, and Return key, Return, are two closely related keys with overlapping and distinct functions dependent on operating system and application. On full-size keyboards, there are two such keys, one in the alphanumeric keys and the other one is in the numeric keys. The purpose of the Enter key is to confirm what has been typed. The return key is based on the original line feed / carriage return function of typewriters. In many word processors, for example, the return key ends a paragraph. In a spreadsheet, it completes the current cell and moves to the next cell. The shape of the Enter key differs between ISO and ANSI keyboards. In the latter, the Enter key is in a single row, usually the third from the bottom, while in the former it spans over two rows and has an inverse L shape. Shift key. Main article, Shift key. The purpose of the Shift key is to invoke the first alternative function of the key with which it is pressed concurrently. For alphabetic keys, Shift and letter gives the uppercase version of that letter. For other keys, the key is engraved with symbols for both the unshifted and shifted result. When used in combination with other control keys, such as Control, Alt or Alt-GR, the effect is system and application dependent. Menu key. Main article, Menu key. The menu key or application key is a key found on Windows-oriented computer keyboards. It is used to launch a context menu with the keyboard rather than with the usual right mouse button. The key's symbol is usually a small icon depicting a cursor hovering above a menu. On some Samsung keyboards the cursor in the icon is not present, showing the menu only. This key was created at the same time as the Windows key. This key is normally used when the right mouse button is not present on the mouse. Some Windows public terminals do not have a menu key on their keyboard to prevent users from right-clicking. However, in many Windows applications, a similar functionality can be invoked with the Shift and F10 keyboard shortcut. Number pad. Many, but not all, computer keyboards have a numeric keypad to the right of the alphabetic keyboard, often separated from the other groups of keys such as the function keys and system command keys, which contains numbers, basic mathematical symbols, for example, addition, subtraction, etc., and a few function keys. In addition to the row of number keys above the top alphabetic row, most desktop keyboards have a number pad or a counting pad on the right-hand side of the keyboard. While numlock is set, the numbers on these keys duplicate the number row. If not, they have alternative functions as engraved. In addition to numbers, this pad has command symbols concerned with calculations such as addition, subtraction, multiplication and division symbols. The Enter key in this keys indicate the equal sign. Miscellaneous. On Japanese / Korean keyboards, there may be language input keys for changing the language to use. Some keyboards have power management keys, for example, power key, sleep key and wake key, internet keys to access a web browser or email, and / or multimedia keys, such as volume controls, or keys that can be programmed by the user to launch a specified application or a command like minimizing all windows. Multiple layouts. It is possible to install multiple keyboard layouts within an operating system and switch between them, either through features implemented within the OS, or through an external application. Microsoft Windows, Linux, and Mac provide support to add keyboard layouts and choose from them. Illumination. Keyboards and keypads may be illuminated from inside, especially on equipment for mobile use. Both keyboards built into computers and external ones may support backlighting. External backlit keyboards may have a wired USB connection, or be connected wirelessly and powered by batteries. Illumination facilitates the use of the keyboard or keypad in dark environments. For general productivity, only the keys may be uniformly backlit, without distracting light around the keys. Many gaming keyboards are designed to have an aesthetic as well as functional appeal, with multiple colors, and color-coded keys to make it easier for gamers to find command keys while playing in a dark room. Many keyboards not otherwise illuminated may have small LED indicator lights in a few important function keys, or elsewhere on the housing, if their function is activated. See photo. See also, ThinkLight. Technology. Main article, Keyboard Technology. Key switches. In the first electronic keyboards in the early 1970s, the key switches were individual switches inserted into holes in metal frames. These keyboards cost from $80 to $120 and were used in mainframe data terminals. The most popular switch types were reed switches, contacts enclosed in a vacuum in a glass capsule, affected by a magnet mounted on the switch plunger. In the mid-1970s, lower-cost direct contact key switches were introduced, but their life in switch cycles was much shorter, rated 10 million cycles, because they were open to the environment. This became more acceptable, however, for use in computer terminals at the time, which began to see increasingly shorter model lifespans as they advanced. In 1978, Keytronic Corporation introduced keyboards with capacitive-based switches, one of the first keyboard technologies not to use self-contained switches. There was simply a sponge pad with a conductive coated mylar plastic sheet on the switch plunger, and two half-moon trace patterns on the printed circuit board below. As the key was depressed, the capacitance between the plunger pad and the patterns on the PCB below changed, which was detected by integrated circuits, IC. These keyboards were claimed to have the same reliability as the other solid-state switch keyboards such as inductive and Hall effect, but competitive with direct contact keyboards. Prices of $60 for keyboards were achieved, and Keytronic rapidly became the largest independent keyboard manufacturer. Meanwhile, IBM made their own keyboards, using their own patented technology. Keys on older IBM keyboards were made with a buckling spring mechanism, in which a coil spring under the key buckles under pressure from the user's finger, triggering a hammer that presses two plastic sheets, membranes, with conductive traces together, completing a circuit. This produces a clicking sound and gives physical feedback for the typist, indicating that the key has been depressed. The first electronic keyboards had a typewriter key travel distance of 0.187 inches, 4.75 millimeters. Key tops were a half-inch, 12.7 millimeters, high, and keyboards were about 2 inches, 5 centimeters, thick. Over time, less key travel was accepted in the market, finally landing on 0.110 inches, 2.79 millimeters. Coincident with this, Keytronic was the first company to introduce a keyboard that was only about 1 inch thick. And now keyboards measure only about a half-inch thick. Key tops are an important element of keyboards. In the beginning, keyboard keytops had a dish shape on top, like typewriters before them. Keyboard key legends must be extremely durable over tens of millions of depressions, since they are subjected to extreme mechanical wear from fingers and fingernails, and subject to hand oils and creams, so engraving and filling key legends with paint, as was done previously for individual switches, was never acceptable. So, for the first electronic keyboards, the key legends were produced by two-shot, or double-shot, or two-color molding, where either the key shell or the inside of the key with the key legend was molded first, and then the other color mold second. But, to save cost, other methods were explored, such as sublimation printing and laser engraving, both methods which could be used to print a whole keyboard at the same time. Initially, sublimation printing, where a special ink is printed onto the keycap surface and the application of heat causes the ink molecules to penetrate and commingle with the plastic modules, had a problem because finger oils caused the molecules to disperse, but then a necessarily very hard clear coating was applied to prevent this. Coincident with sublimation printing, which was first used in high volume by IBM on their keyboards, was the introduction by IBM of single curved dish keycaps to facilitate quality printing of key legends by having a consistently curved surface instead of a dish. But one problem with sublimation or laser printing was that the processes took too long and only dark legends could be printed on light-colored keys. On another note, IBM was unique in using separate shells, or keycaps, on keytop bases. This might have made their manufacturing of different keyboard layouts more flexible, but the reason for doing this was that the plastic material that needed to be used for sublimation printing was different from standard IBM keytop plastic material. Three final mechanical technologies brought keyboards to where they are today, driving the cost well under $10. One monoblock keyboard designs were developed where individual switch housings were eliminated and a one-piece monoblock housing used instead. This was possible because of molding techniques that could provide very tight tolerances for the switch plunger holes and guides across the width of the keyboard so that the key plunger to housing clearances were not too tight or too loose, either of which could cause the keys to bind. 2. The use of contact switch membrane sheets under the monoblock. This technology came from flat panel switch membranes, where the switch contacts are printed inside of a top and bottom layer, with a spacer layer in between, so that when pressure is applied to the area above, a direct electrical contact is made. The membrane layers can be printed by very high volume, low-cost reel-to-reel printing machines, with each keyboard membrane cut and punched out afterwards. Plastic materials played a very important part in the development and progress of electronic keyboards. Until monoblocks came along, GE's self-lubricating Delrin was the only plastic material for keyboard switch plungers that could withstand the beating over tens of millions of cycles of lifetime use. Greasing or oiling switch plungers was undesirable because it would attract dirt over time which would eventually affect the feel and even bind the key switches, although keyboard manufacturers would sometimes sneak this into their keyboards, especially if they could not control the tolerances of the key plungers and housings well enough to have a smooth key depression feel or prevent binding. But Delrin was only available in black and white, and was not suitable for keytops, too soft, so keytops use IBM plastic. However, as plastic molding advanced in maintaining tight tolerances, and as key travel length reduced from 0.187 inch to 0.110 inch, 4.75 mm to 2.79 mm, single-part keytop /plungers could be made of IBM, with the keyboard monoblocks also made of IBM. In common use, The term mechanical keyboard refers to a keyboard with individual mechanical key switches, each of which contains a fully encased plunger with a spring below it and metallic electrical contacts on a side. The plunger sits on the spring, and the key will often close the contacts when the plunger is pressed halfway. Other switches require the plunger to be fully pressed down. The depth at which the plunger must be pressed for the contacts to close is known as the activation distance. Analog keyboards with key switches whose activation distance can be reconfigured through software, optical switches that work by blocking laser beams, and Hall effect keyboards that use key switches that use a magnet to activate a Hall sensor are also available. Some keyboards, called pressure sensitive, allow varying input according to the distance pressed, analogously to the analog joystick. Control processor. Computer keyboards include control circuitry to convert key presses into key codes, usually scan codes, that the computer's electronics can understand. The key switches are connected via the printed circuit board in an electrical XY matrix where a voltage is provided sequentially to the Y lines and, when a key is depressed, detected sequentially by scanning the X lines. The first computer keyboards were for mainframe computer data terminals and used discrete electronic parts. The first keyboard microprocessor was introduced in 1972 by General Instruments, but keyboards have been using the single-chip 8048 microcontroller variant since it became available in 1978. The keyboard switch matrix is wired to its inputs, it converts the keystrokes to key codes, and, for a detached keyboard, sends the codes down a serial cable, the keyboard cord, to the main processor on the computer motherboard. This serial keyboard cable communication is only bidirectional to the extent that the computer's electronics controls the illumination of the caps lock, num lock and scroll lock lights. One test for whether the computer has crashed is pressing the caps lock key. The keyboard sends the key code to the keyboard driver running in the main computer. If the main computer is operating, it commands the light to turn on. All the other indicator lights work in a similar way. The keyboard driver also tracks the shift, alt and control state of the keyboard. Some lower quality keyboards have multiple or false key entries due to inadequate electrical designs. These are caused by inadequate key switch debouncing or inadequate key switch matrix layout that don't allow multiple keys to be depressed at the same time, both circumstances which are explained below. When pressing a keyboard key, the key contacts may bounce against each other for several milliseconds before they settle into firm contact. When released, they bounce some more until they revert to the uncontacted state. If the computer were watching for each pulse, it would see many keystrokes for what the user thought was just one. To resolve this problem, the processor in a keyboard, or computer, debounces the keystrokes, by aggregating them across time to produce one confirmed keystroke. Some low-quality keyboards also suffer problems with rollover, that is, when multiple keys pressed at the same time, or when keys are pressed so fast that multiple keys are down within the same milliseconds. Early solid-state key switch keyboards did not have this problem because the key switches are electrically isolated from each other, and early direct contact key switch keyboards avoided this problem by having isolation diodes for every key switch. These early keyboards had N-key rollover, which means any number of keys can be depressed and the keyboard will still recognize the next key depressed. But when 3 keys are pressed, electrically closed, at the same time in a direct contact key switch matrix that doesn't have isolation diodes, the keyboard electronics can see a 4th phantom key which is the intersection of the X and Y lines of the 3 keys. Some types of keyboard circuitry will register a maximum number of keys at one time. 3-key rollover, also called phantom key blocking or phantom key lockout, will only register 3 keys and ignore all others until one of the 3 keys is lifted. This is undesirable, especially for fast typing, hitting new keys before the fingers can release previous keys, and games designed for multiple key presses. As direct contact membrane keyboards became popular, the available rollover of keys was optimized by analyzing the most common key sequences and placing these keys so that they do not potentially produce phantom keys in the electrical key matrix. For example, simply placing 3 or 4 keys that might be depressed simultaneously on the same X or same Y line, so that a phantom key intersection /short cannot happen, so that blocking a third key usually isn't a problem. But lower quality keyboard designs and unknowledgeable engineers may not know these tricks, and it can still be a problem in games due to wildly different or configurable layouts in different games. Connection types. There are several ways of connecting a keyboard to a system unit, more precisely, to its keyboard controller, using cables, including the standard AT connector commonly found on motherboards, which was eventually replaced by the PS/2 and the USB connection. Prior to the iMac line of systems, Apple used the proprietary Apple Desktop Bus for its keyboard connector. Wireless keyboards have become popular. A wireless keyboard must have a transmitter built in, and a receiver connected to the computer's keyboard port. It communicates either by radio frequency, RF, or infrared, IR, signals. A wireless keyboard may use industry-standard Bluetooth radio communication, in which case the receiver may be built into the computer. Wireless keyboards need batteries for power, and may be at risk of data eavesdropping. Wireless solar keyboards charge their batteries from small solar panels using natural or artificial light. The 1984 Apricot Portable is an early example of an IR keyboard. Alternative text entering methods. Optical character recognition, OCR, is preferable to rekeying for converting existing text that is already written down but not in machine-readable format, for example, a linotype composed book from the 1940s. In other words, to convert the text from an image to editable text, that is, a string of character codes, a person could retype it, or a computer could look at the image and deduce what each character is. OCR technology has already reached an impressive state, for example, Google Book Search, and promises more for the future. Speech recognition converts speech into machine-readable text, that is, a string of character codes. This technology has also reached an advanced state and is implemented in various software products. For certain uses, for example, transcription of medical or legal dictation, journalism, writing essays or novels, speech recognition is starting to replace the keyboard. However, the lack of privacy when issuing voice commands and dictation makes this kind of input unsuitable for many environments. Pointing devices can be used to enter text or characters in contexts where using a physical keyboard would be inappropriate or impossible. These accessories typically present characters on a display, in a layout that provides fast access to the more frequently used characters or character combinations. Popular examples of this kind of input are Graffiti, Dasher and on-screen virtual keyboards. Other issues. Keystroke logging. Unencrypted wireless Bluetooth keyboards are known to be vulnerable to signal theft by placing a covert listening device in the same room as the keyboard to sniff and record Bluetooth packets for the purpose of logging keys typed by the user. Microsoft Wireless Keyboards 2011 and earlier are documented to have this vulnerability. Keystroke logging, often called keylogging, is a method of capturing and recording user keystrokes. while it is used legally to measure employee productivity on certain clerical tasks, or by law enforcement agencies to find out about illegal activities, it is also used by hackers for various illegal or malicious acts. Hackers use keyloggers as a means to obtain passwords or encryption keys and thus bypass other security measures. Keystroke logging can be achieved by both hardware and software means. Hardware keyloggers are attached to the keyboard cable or installed inside standard keyboards. Software keyloggers work on the target computer's operating system and gain unauthorized access to the hardware, hook into the keyboard with functions provided by the OS, or use remote access software to transmit recorded data out of the target computer to a remote location. Some hackers also use wireless keylogger sniffers to collect packets of data being transferred from a wireless keyboard and its receiver, and then they crack the encryption key being used to secure wireless communications between the two devices. Anti-spyware applications are able to detect many keyloggers and cleanse them. Responsible vendors of monitoring software support detection by anti-spyware programs, thus preventing abuse of the software. Enabling a firewall does not stop keyloggers per se, but can possibly prevent transmission of the logged material over the net if properly configured. Network monitors, also known as reverse firewalls, can be used to alert the user whenever an application attempts to make a network connection. This gives the user the chance to prevent the keylogger from phoning home with his or her typed information. Automatic form-filling programs can prevent keylogging entirely by not using the keyboard at all. Historically, most keyloggers could be fooled by alternating between typing the login credentials and typing characters somewhere else in the focus window. Keyboards are also known to emit electromagnetic signatures that can be detected using special spying equipment to reconstruct the keys pressed on the keyboard. Neil Farrell, Executive Director of the Identity Theft Council, revealed to Information Week that more than 25 years ago, a couple of former spooks showed me how they could capture a user's ATM PIN from a van parked across the street, simply by capturing and decoding the electromagnetic signals generated by every keystroke, Farrell said. They could even capture keystrokes from computers in nearby offices, but the technology wasn't sophisticated enough to focus in on any specific computer. Physical injury. The use of any keyboard may cause serious injury, that is, carpal tunnel syndrome or other repetitive strain injury, to hands, wrists, arms, neck or back. The risks of injuries can be reduced by taking frequent short breaks to get up and walk around a couple of times every hour. As well, users should vary tasks throughout the day, to avoid overuse of the hands and wrists. When inputting at the keyboard, a person should keep the shoulders relaxed with the elbows at the side, with the keyboard and mouse positioned so that reaching is not necessary. The chair height and keyboard tray should be adjusted so that the wrists are straight, and the wrists should not be rested on sharp table edges. Wrist or palm rests should not be used while typing. Some adaptive technology ranging from special keyboards, mouse replacements and pen tablet interfaces to speech recognition software can reduce the risk of injury. Pause software reminds the user to pause frequently. Switching to a much more ergonomic mouse, such as a vertical mouse or joystick mouse, may provide relief. By using a touchpad or a stylus pen with a graphic tablet, in place of a mouse, one can lessen the repetitive strain on the arms and hands. See also: one keyboard computer, popular form of computers in the early 1980s. 2 digital pen. 3 Dvorak. 4 IBM PC keyboard. 5 keyboard layout. 6 keyboard protector. 7 keyboard technology. 8 keypad. 9 Moltron. 10 numeric keypad, 11 overlay keyboard, 12 table of keyboard shortcuts, 13 virtual keyboard, touchscreen keyboard. References.